Welcome, everyone. Welcome to today's webinar. Thank you so much for attending. My name is Tanya Mendoza, and I'm the product manager with RD Abbott. Today's webinar topic is on Hallstar plasticizers and magnesium oxides. To get started, let's go over a couple of housekeeping items. While your videos and microphones have been disabled, you're more than welcome to submit questions and chat with our panelists throughout the presentation. At the end of the presentation, I'll present your questions anonymously to Sean and Jim. To chat with our panelists, click on the chat icon at the bottom of your Zoom screen. Type your message in the designated area, and then press enter. To send us a question, just click on the Q&A icon at the bottom of your Zoom screen, type your question in the designated area, then press enter or click the send button. For those unfamiliar with RD Abbott, we are a materials science, engineering, and distribution company that's been serving the rubber industry since 1948. We are staffed with rubber experts, equipped with US-based laboratory and manufacturing facilities, and stocked with premium elastomer products in warehouses throughout North America. Our product line encompasses a broad list of elastomers, rubber chemicals, and dispersions, plasticizers, fillers, bonding agents, and testing equipment, all from respected manufacturers with trusted name brands. Curiosity is at the root of nearly every business decision and strategic action we take at RD Abbott. It's how we approach every technical inquiry and sales opportunity, and it's modeled in our genuine desire to serve our customers and suppliers efficiently and effectively. Today's curiosity is modifying polymers with plasticizers and magnesium oxides, and we're honored to have Sean Neuenfeldt and Jim Koslowski from Hallstar to address this topic. Sean Neuenfeldt currently works as a manager of technology and products as part of Hallstar's industrial polymer modifiers team, with a focus on new development. Sean is the lead technical resource for X8 solvents and is skilled in polymer rheology, thermoplastic compounding, and automotive coatings formulations. He earned his Bachelor of Science in Biochemistry from Michigan State University and his Master of Science in Chemistry from Oakland University.
Thanks for the introduction, Tanya.
Thank you, Sean. Jim Koslowski is a commercial associate for Hallstar Industrial Solutions with both sourcing and sales responsibilities. Jim's background is in polymer synthesis for polyurethane coatings. He has a Bachelor of Science in Chemistry from Northern Illinois University. We look forward to hearing from both of you today.
Thank you, Tanya. Appreciate it.
Thank you, Jim.
All right. Hi, everyone. My name is Jim Koslowski, and I would like to thank you again for attending this webinar on polymer modification for elastomers. Sean and I will present to you Hallstar's background and expertise in elastomer modification. We will also discuss our brand of magnesium oxide under the trade name Maglite. Hallstar is a market-leading manufacturer of specialty ester plasticizers. Hallstar works closely with customers to identify the key performance requirements to optimize their end product. We have decades of experience in plasticizer compatibility in elastomers, and will collaborate with technical and commercial teams to find the right product for any project. Here's an overview of Hallstar's key developments and acquisitions. In 1986, the Hallstar company was founded by our current leadership team and has expanded ever since. With 2 divisions, we cover a wide range of markets in the personal care and industrial space. In 2009, Hallstar acquired the Dioplex and Resilube product lines from Dow Chemical, as well as the TP series in 2012. Since that time, Hallstar has continued to develop new products for the industrial polymer market. At the core of Hallstar's vision is people. Hallstar is a small privately held company that cultivates supplier and customer relationships. We are committed to ethical and sustainable practices in everything we do. Hallstar continues to develop safe and efficient processes to better serve our customers. Hallstar is a global specialty manufacturer. We are headquartered in Chicago, Illinois, with research and development centers located in the US, Europe, Asia, and South America. Our main production facility is in Bedford Park, Illinois, and with over 4 decades of experience, Hallstar holds over 100 patents. Hallstar's core markets can be divided evenly between industrial and beauty and personal care. Our beauty and personal care division serves sun and skincare solutions, whereas our industrial team serves elastomers, thermoplastics, adhesives, and more. Elastomers and thermoplastics make up a majority of industrial's key portfolio. Hallstar specializes in identifying the optimal product for a specific customer application. With our deep knowledge of polymer compatibility, Hallstar can custom design a polymer modifier for a specific performance application. With decades of research experience in applications testing, Hallstar will determine the best product that is not over or under designed. Hallstar offers approximately 100 specialty ester products as we continue to learn, synthesize, and scale up new plasticizers in the polymer marketplace. Hallstar offers most products in liquid or dry silica form. The dry silica form aims in handling and processing. For any beer drinkers out there, you can think of Hallstar as a craft beer manufacturer. At this time, I'd like to pass this over to my colleague, Sean Neuenfeldt, for his portion of the presentation. Sean will present plasticizer elastomer combinations. Thanks, Sean.
Thanks, Jim. Thanks for the introduction. All right, so briefly, I wanted to introduce ester chemistry and ester chemistry 101. So for those of you who aren't familiar, the reaction that Hallstar is generally running for a lot of our products are reacting a carboxylic acid with an alcohol. When we react those two products, we're forming an ester bond, and we're going to get water as our byproduct. So a very simplified diagram of this is in front of us. Carboxylic acid with an alcohol, getting ourselves an ester. This is a very simplified diagram, but generally the process that we're running. What I wanted to be able to show in what is an ester is the different types of ester chemistry and how Hallstar generally divides these different categories. Generally, we divide these into monomeric ester chemistries and polymeric ester chemistries. Monoesters, diesters, and triesters all fall into the category of monomeric ester chemistries. While they have 1, 2, or 3 ester bonds, there's still going to be a single monomeric molecule. Hallstar has a lot of these different monomeric ester chemistries, but really specializes in polymeric and polyester chemistries. With that, we're using either a di or trifunctional carboxylic acid, and we're using a different group of glycols and alcohol terminators or acid terminators, and building low, medium, and high molecular weight polyester chemistries. When you have a higher molecule, generally the higher molecular weight will give you a higher viscosity and greater permanence in the polymer. Generally, the higher molecular weight you get, the higher it's going to be in terms of extractability and volatility to heat, while additional branching is going to give you better extractability to different oils and chemical resistance, so extraction to those different molecules. Monoesters being the best for low temperature flexibility and best for low temperature plasticizing efficiency, while the polyesters and polymeric molecules are going to be the best for extraction resistance, durability, higher tensile strength, and those sort of characteristics. So the different sort of ester functionality that we're doing is primarily lowering the modulus. So your M10 is how much PSI or tensile strength is going to be required to elongate a segment of either a thermoplastic or elastomer a set distance. And M10 would be to measure the modulus at 10% elongation, while 100 would be 100% elongation. The image on the right is an image of our Instron tensiometer we have in-house on some PVC, just showing the different tensile tests that we run here. We're also interested in increasing the elongation, how far some of this material will stretch, or lowering the glass transition, so that TG of the material, where it transitions from a more brittle product to a more flexible product, and increase the functional temperature range at these different polymers can function at. This is going to be a lot of times application dependent, but very, very important for the different sort of plasticizer recommendations that we're making. We also have certain products that increase cohesion also. So different substrates, bonding those to each other. Ester plasticizers can do a magnitude of different sort of performance and polymer modification. So we don't want to think of this simply as a way to lower the glass transition temperature, but to bring about a lot more functionality to your base polymer. The general ester synthesis pathway is to act as an alcohol, carboxylic acid, and glycol to a premix tank where it would be heated and melted, all solids melted. That's going to react at over 180 Celsius, and we're going to get water as a byproduct. We're going to have some acid and alcohols that are going to be recovered and stripped off and recycled into our stream. So our process is a very efficient manufacturing process. Once we have our ester, or be it a monoester, diester, triester, or polyester, we're going to go through a post-drying step where we're going to remove any excess water. We're going to deodorize it, decolorize it. So you're going to have a very clean, very homogeneous polyester with very little monomer content in there at very good color levels, depending on the application, and a very consistent product. That product will then go to a filtration where we're going to make sure no solids or any sort of particulates are in there. So we got a very nice water white, clean product. And then that'll be going to any sort of packaging, be it drums, be it totes, or bulk containers. We have the ability to do any of that packaging. So briefly looking at our different product lines, I wanted to divide this up into a couple categories. Generally, this is going from left to right in increasing molecular weight, while the chemistries of these differ quite significantly. The first one I want to talk about is our X8 product line. This is a line of acetate ester solvents. These solvents are low molecular weight monoesters. They're acetic and hydride reacted with Exxon alcohols. And these have high branching EPA 4B clearance for organic farming. These have low hazard, low odor solvents, so offering an interesting alternative. These are functional in acrylics, epoxies, high polarity PMMA, polyesters, and polyurethane. So these primarily function as solvents due to their volatility. Our Plastol product line is traditionally our monomeric, monoester chemistries. These are typically monoesters or diesters, and typically are monomeric in nature. So these typically are focusing on low temperature flexibility properties and more so than durability. So these have a very high polarity range. We have things that go into very high polarity nylon and all the way down to polyethylene. So there are a magnitude of Plastol products. This includes some more of the commoditized products too, your dioctyl adipate, dioctyl sebacate, and any residual products, any sort of DIMP or any sort of medium to high molecular weight phthalates. The TP series is going to be in the Tegamer series are going to be combinations of monomeric ether ester chemistries. And these are going to be unique where they really specialize both in high temperature requirements and really, really effective low temperature flexibility. And that's really due to the ether linkages in those sort of chemistries. So those are very, very excellent product lines for more high polarity elastomer systems. Hallstar also has a line called Hallgreen, which is going to be a line of 100% bio-based polyesters. These have ASTM D6400, so they have ASTM tests that certify their biodegradability, and they're USDA certified bio-based with all plant-based raw materials. These are also on the higher polarity side, so typically designed for either higher ACN content elastomers or different sort of high polarity thermoplastic systems. And we'll go more into depth into some of those different polymer systems later. On the far right, you have our Diaplex D, Plastol P, and Paraplex A and G product lines. Those product lines are going to be primarily high molecular weight polyester chemistries and are often used in vinyl interiors for automotive, where extraction is going to be critical. Often used in wire and cable and automotive underhood due to the polymeric nature of these and the low extractability of these chemistries. These really focus on improved durability, extraction resistance to solvents, oils, degradation resistance to either ozone or UV, and migration resistance to any sort of substrates that may be in contact with these parts. Traditionally, we use our Diaplex, Plastol P, and Paraplex A and G lines. We see these frequently in HNBR, NBR, and PVC. I talked about these product lines briefly, but I kind of wanted to show the general polarity of these. At the bottom here, we traditionally had esters that were based on polyethylene, and the different sort of polarities of elastomers would be going up and down on the y-axis here. We can see that products like BSA are only going to be applicable to high polarity elastomers such as nylon, but we can see that many of our polymerics here are grouped in this middle area. This is going to kind of be our middle ACN content, HNBR or MBR. And we see good compatibilities with these systems with many of our polymeric systems or many of our polymeric plasticizers. We could see that due to the nature of the ester bond and the high polarity of the ester bond, that traditionally monomeric in monoester, diester, and triester chemistries are traditionally lower polarity than polymeric chemistries. Polyesters and polymeric plasticizers in general have a higher polarity than monomeric esters. So that's where we see this fairly tight grouping of plasticizers here on the far right. Looking at a lot of Hallstar's markets and Hallstar Industrial's markets, we did a little bit of a breakdown here into our different market segments. The one we're looking at first is our elastomer segment. That'll be most applicable here at 35 to 40%. This is going to be automotive belts, hoses, seals, gaskets, oil and gas drilling seals, print rolls and blankets, conveyor belts, tires, and wire and cable. Other markets include PVC, which has a lot of different applications, automotive interiors being one requiring higher durability, flexible tubing and hose, conveyor belts that may require extraction resistance to food oils or have to have 21 CFR requirements. All these are going to be requirements for higher durability plasticizers. Other groups are ACS, which is adhesives, sealants, and coatings. Those polymer systems there, and lubricants, making up 2% of the Hallstar market. So for this presentation, we wanted to look at the elastomers that are going to be major users of plasticizers and get a little bit of a better understanding about what sort of plasticizers would go into these elastomer compounds and why we're looking at those different plasticizers and those compounds and why they make sense. So the ones that we're going to be primarily looking at in this order is going to be nitrile rubber, hydrogenated nitrile butadiene rubber, acrylic elastomers, including AEM and ACM, polychloroprene, and chlorinated polyethylene. So the first segment that we want to look at is going to be nitrile rubber. And this is going to be a fairly high user of plasticizers. Nitrile rubber in general is going to be focused on extraction to oil. So in general, the composition of nitrile rubber is going to be a copolymer of acrylonitrile and butadiene. So the first thing when we're looking at a plasticizer selection is going to be looking at that ratio of acrylonitrile to butadiene. The higher the acrylonitrile content in here, the higher the polarity. So you could have a nitrile-based polymer and have compatibility with one plasticizer at a certain ACN content, but have no compatibility with that same plasticizer at a different ACN content. So this ratio matters very, very much. Traditionally, the acrylonitrile content ranges from 19 being a very low polarity system to 51 being a fairly high polarity system. We generally see that a lot of our polyesters are going to be really compatible with nitrile. These polymers and the polymeric nature of a lot of the esters and the polyesters that Hallstar synthesizes are going to be more polar than a lot of the monomeric chemistries. So in general, when you're trying to substitute in a polymeric chemistry for a monomeric chemistry, you're going to probably have improved compatibility just based on the polarity of the base polymer and the plasticizer. You could do other things that are going to be able to maintain that plasticizer within the elastomer better, but in general, the polarity of the elastomer and the base plasticizer is going to really control any sort of exudation or blooming to the surface. So for nitrile, our applications that we're really going to be looking into are going to be applications that are going to have very high oil extraction. So we're seeing hydraulic hoses, adhesive printing rolls, transformer seals. These are aerosol seals, appliance seals, and there are different sort of gaskets and seals a lot of times that need some sort of oil swell. So when we're looking at nitrile rubber, a lot of times people are going to be using monomeric chemistries because they're going to require some sort of volume swell in their nature. So the part usually does require a slight amount of swelling. A lot of times phthalates are used in this because they do offer a balance of volatility resistance, moisture resistance, and acid chemical stability. But a lot of times there's going to be regulations that are going to be pushing out phthalate chemistry. So while phthalates are used very often in this, they might not be the best plasticizer selection for this elastomer. So like I mentioned, traditionally monomeric plasticizers are going to be used in these sort of applications. They need to have that fuel oil resistance as well as abrasion resistance. Plasticizers really help that low temperature flexibility and have really, really excellent flexibility. So some of our popular product choices we have in this field are Plastol 7050. That's going to be one of our lower polarity monomeric ester chemistries. And we like that one because it improves upon some of the benefits of nitrile rubber. It gives very, very high oil resistance, and this is naturally not susceptible to migration and really gives excellent low temperature flexibility. This would be for likely something with a lower ACN content, the Plastol 750. The TP95 has excellent oil aging, and TP90B has the lowest TG of some of any of our esters we have. The TP90B has both ether and ester bonds in it, so giving it really, really some low temperature flexibility and is really going to be superior to any straight ester chemistry in terms of low temperature flexibility. Those ether ester bonds allow it to have some really unique and novel low temperature flexibility characteristics. In nitrile, it's not just monomeric ester chemistries. We do have polymeric plasticizers also. So those requirements where you have to have a lot of resistance to oil, you might see water, heat, polymeric plasticizers are going to be our best option. Some of our popular choices are going to be some of our flagship products, including our Paraplex A8000, A8200, Paraplex A8600 for retention of physical properties after aging. So not only do you get the physical properties that you're looking to start with, but you're maintaining those properties after plasticizer has been extracted from oil or heat or temperature. With a monomeric ester chemistry, all of that plasticizer will be removed with heat or oil, and you'll see it in the weight loss. With these sort of chemistries, you'll see very, very little weight loss. And so you'll be able to retain a lot of those tensile properties that you're looking for. Other chemistries like the Diaplex 100, the 904, and the VLV all offer excellent original physical properties and oil resistance. So when we're looking at nitrile, we're really trying to pair up the good parts of the plasticizer with the positives of the base elastomer. And that's why a lot of these sort of product recommendations are centered upon the resistance to oil. I mentioned before that phthalates are commonly used in nitrile, which is true. They are the #1 plasticizer by volume for nitrile. But we understand at Hallstar that there's a strong push to eliminate phthalates. We have the ability, and we've developed a lot of ester chemistries and polyester chemistries to go and mimic the performance of phthalates and being able to offer fully aliphatic polyesters to be able to remove these from your system and be able to have a drop-in replacement. Some of the examples of this are PRA 126, our PRA 200, and our PRA 217. All of these being able to offer performance equivalents to DIDP, DINP, and DOP. So all of these will be di, and then they'll have some sort of, they'll be difunctional phthalates with different sort of end caps on these. So these will be all diesters, the DIDP, DINP, and DOP, and all of these that we have are non-phthalate replacements. Some of our other options are PRA 610 is an option for 100% renewable raw material. And so the idea here is that not only is it a replacement for phthalates, but it's not even a petro-derived polyester. So some of these, not only are you able to replace the petro-derived phthalate, we could replace a petro-derived phthalate with a bio-based raw material and being able to match the performance or even improve the performance of the nitrile. One of our case studies we had for nitrile was the resistance to various engine oils. So we did a study where we went and immersed some NBR in 901 and 902 oil to see how different oils are going to extract. We see that Plastol 7050 provides an excellent balance of oil and low temperature properties. TP95 and TP90B both offer that high performance monomeric volatility, which is somewhat rare for a monomeric chemistry, but also gives that really excellent low temperature flexibility that we mentioned based on that ether incorporating into that nitrile. An example of Paraplex A8000 is where you have a polyester that's able to offer that same excellent oil extraction. It may not have as good of that low temperature flexibility, but because of that high molecular weight and the high viscosity of that polyester, we're able to become more entangled in that base elastomer and become less extractable. Another example is looking at head gaskets. So head gaskets also have to be in contact with oil, has to have good compression set, and have to have a wide range of temperature conditions. So we saw that the 7050 is able to provide that by offering that high heat and oil resistance. Chemistries like the TP759 or the 90B may not be able to be the appropriate product for a head gasket, but it's all going to be application dependent. It's all going to determine on what sort of conditions that part is going to see. If it's going to see more oil extraction, we would likely recommend something that's more branched. If it's something that's going to see heat, we would probably recommend something that is a higher molecular weight. Some applications will require both, and so we might have to have something highly branched, high molecular weight. It's always going to be a trade-off between different sort of performance properties, so understanding the application, understanding the performance requirements are going to be key. The next polymer system that I want to talk about is hydrogenated nitrile butadiene rubber, commonly called HNBR. So for this, hydrogenation, it results in a highly saturated base polymer. So the NBR is the diagram on the top right, and it shows your acrylonitrile and your butadiene. When you hydrogenate some of the nitrile and butadiene, or the NBR, you're going to get that butadiene unit is going to be fully hydrogenated, and that double bond is going to change to a single bond, and it's going to give it inherent ozone protection. It's going to dictate applicable cure systems. So without that double bond, certain grades can only be peroxide cured and won't be able to be sulfur cured. It has a wider operating temperature because of this performance. because it doesn't have that unsaturation in the backbone, we're able to get to higher temperatures with that base polymer. So 165 Celsius. So this is high. The acrylonitrile, or the ACN level that gives that polarity, is still going to vary from 17 to 50, because the thing that we're hydrogenating is going to be the butadiene linkage and not the acrylonitrile unit. So that ACN content is still going to stay the same. You're still going to have a range of polarities and compatible plasticizers with HNBR also. That'll also give varying oil and chemical resistance depending on the grade chosen. And these have really excellent physical properties and the retention of properties in various environments. So really a focus on higher durability, higher, harsher environments that it's going to see versus nitrile. So listing some of the applications again, we're looking at hoses. So air conditioning hoses, biodiesel, fuel, hydraulic hoses, oil field, pump station, wheel-held seals, packers, and blowout preventers. So the focus on these being a little bit more on outdoor applications, things that require that ozone resistance to not become brittle. So by removing that unsaturation from the base polymer, we're able to go and have that base polymer be more applicable in other sort of applications. And so what we naturally have to do is change the plasticizer that we use. Briefly, I wanted to touch on some of the Arlanxeo elastomer brands that are distributed by RD Abbott. That includes nitrile, the Krynac and the Probunin, and HNBR, which is the Thurban. Going back a little bit to HNBR, we wanted to explain why some of these products were going to be the best products for HNBR. And some of the ones that we chose were our Paraplex A8200, our Paraplex A8600, and our Tegmer 812. The reason we wanted to choose this is because they had to have that higher heat requirement. With HNBR, these were likely going to see exposure to outdoors, that higher temperature requirement that would see outside of NBR. And so naturally, we had to build the molecular weight. Products we previously recommended, like our Paraplex A1000, we would not recommend for this application. We would focus more on the higher molecular weight equivalents, like our Paraplex A8200 or A8600, which offer a much higher molecular weight for those conditions that this elastomer will see. Our Tegmer 812 is going to be one of our highest molecular weight Tegmer products, again, offering that low temperature flexibility because of that ether bonds in there, ether ester bonds, and building that molecular weight to give it that heat resistance. So one of the case studies for HNBR is looking at the powertrain belt. This belt is going to be exposed to temperatures higher than would be permissible for nitrile. So this is going up to 140 Celsius. It has to have oil resistance because this is going to be under the hood application, but also requires flexibility at -40 degrees Celsius. So an ester plasticizer of this application has to be able to maintain that low temperature after the exposure to heat. So any monomeric ester chemistry, any phthalates that you would be able to put in there may be compatible initially, but not after temperature. So with some of these belts having to get 100,000 to 150,000 miles, in year 2 or 3 of owning the car might see extreme heat under the hood. And after 10, 20 years, you need to be able to be sure that that belt isn't going to tear and it's going to be able to maintain that -40 C flexibility. So when you have a very cold day here in Chicago, your belt's not going to break right away when you go outside. So some of our solutions is our Tegmer 812. This is what I mentioned in our previous slide as an ether ester, high molecular weight, very polar plasticizer. This is one of the very specialty products Hallstar carries that's not just an aliphatic polyester, but really is able to incorporate both ether and ester bonds here, giving a very high molecular weight monomeric ester, but giving it a really nice balance of low temperature flexibility and heat resistance. So kind of hitting both ends of the spectrum here. And a lot of times these are very, very efficient molecules. So you'll only need a very low amount to achieve the required physical properties. A lot of these plasticizers don't need to be used as primary plasticizers, but can be used to supplement the plasticizer package that's already in there. These can be used in conjunction with many sort of ester chemistries. So if you're already using some sort of plasticizer in your system, these will likely have compatibility with your system as long as they have compatibility with the base polymer. The next elastomer system I want to talk about is acrylic elastomers, specifically AEM and ACM. In general, acrylic elastomers are made up of three backbones or three monomers in the backbone: ethyl acrylate, butyl acrylate, methoxy ethyl acrylate, each giving different performance features in the backbone. So something I wanted to show here is how there are options to modify the base elastomer to give some sort of different properties. But a lot of times the base polymer system will have already been selected. So this is why some of these might come with intrinsic natural abilities. Some methoxy ethyl acrylate acrylic elastomer may have poor heat resistance, but that's why you might have to go and balance out that properties with a select plasticizer. So for AEM, ACM, a lot of the applications we see are the ones requiring even higher heat than HNBR. So these are going to be automotive transmission seals. This is going to be turbochargers, hoses and ducts, oil cooler hoses, oil pan, and cam cover gaskets. So really, these are going to have to have very high oil, heat, flame, and it's going to have a really high temperature range. So you're going to have to be able to also pair up a plasticizer that would match with this. So with some of these acrylic elastomers having to get over 175 Celsius, while a lot of polyester plasticizers and plasticizers in general will be compatible with this polymer system, there are very few plasticizers that are going to be able to maintain this temperature rating. So while a lot of plasticizers you're going to be able to mix into an acrylic system, those are all going to be fully extracted at the operating temperatures that a lot of these elastomer systems have to operate at. So these are typically seen in very small engines that have to run very, very hot. These have to have both that oil extraction and still have to have some low temperature properties to be able to maintain those properties after heat exposure to 175 degrees C. Some of our best choices are TP759, which will give you that low temperature properties, or we could even move over to our Tegmer product line. We mentioned that before as a very high molecular weight, still monomeric ester chemistry, both ether and ester bonds here, able to offer above that 175 Celsius operating temperature range. So we might have to, in some of these applications, build the molecular weight very, very high just to be able to meet the operating temperatures of these elastomers. So it's more than just finding the equivalent polarity ranges of these systems. Also, like we mentioned before, we have products like our A series, so our Paraplex A8000, our Paraplex A8200, and our Paraplex A8600. All of those Paraplex products will be compatible in these systems. They may not have as good of low temperature flexibility as the Tegmer product lines, but will have their own sort of benefits. So while we have a lot of different compatible systems, AEM and ACM will strictly need to focus on very high molecular weight ester options. One of the examples here is turbochargers. So for this application, we want to look at smaller engines. These smaller engines, V4 cylinders, have been replacing a lot of the V6 and V8 engines in traditional internal combustion engines for improved fuel economy. These, because of the size, have to operate at higher temperatures under very severe conditions, but also need that low temperature flexibility to be able to operate in cold temperatures. So some of those are Tegmer or TP759, which gives that low temperature properties, and our Tegmer 812, which will give a very wide operating temperatures, both on the low and the high end of the spectrum. Paraplex A8600 would be a polymeric ester with a really focus on that fluid resistance and that permanence. So a lot of our Paraplex A series would be more focusing on adipic acid-based carboxylic acids and really excel in that fluid resistance and that permanence. Another system that I wanted to look at was polychloroprene. Polychloroprene is made by the polymerization of chloroprene to polychloroprene and is primarily by free radical emulsion. So this primarily uses monomeric ester chemistry. And one of the reasons for that is going to be the low polarity of the base polymer. With this system, you're going to have it be relatively on the low polarity end of our scale. And so a lot of our traditional polyester chemistries that are typically higher polarity and excellent for nitrile might not work as well in this situation. These, by nature of the ester bond, might have to use mono or diester chemistries. These are traditionally, some of the applications are expansion joints, escalator handrails, shoe soles, water seals, and wire and jacket cabling. Primarily the monomeric esters are really going to be used in this situation to give it that low temperature flexibility. A little less focused on the durability aspect of this, but Hallstar does have a wide variety of products that would be both compatible in this system and be improvements over any sort of low polarity process oils that might be used in this sort of base polymer. One example is our Plastol 100, which really works excellent by providing an oil extraction, heat resistance, flame resistance, and abrasion resistance. And we see abrasion being one of the main requirements for this. So that's also something plasticizers could really do. Instead of having to use naphthenic oil or a process oil, you could improve and use something like a Plastol 100, which would give you still that low temperature flexibility and much improved abrasion resistance. So the last polymer system that I really wanted to look into was chlorinated polyethylene. I'm going to abbreviate it here, CPE. So CPE is produced from high density polyethylene that's randomly chlorinated in aqueous slurry. So you'll have HDPE, and you're going to randomly chlorinate it along the polymer backbone. Generally, the chlorine content will range from 25 to 42% by weight. And some of the advantages of including that chlorine onto the backbone is it gives very, very good resistance to ozone, oxidation, abrasion, and flex cracking. So we see a lot of these being really excellent in outdoor applications. We see it in roofing membranes, maybe outdoor wire and cable jacketing, geomembranes, automotive, industrial hoses, tubings, things that'll be outside and might be exposed to ozone oxidation. Some of the products and plasticizers that we recommend for that is our Plastol 670, which is going to be a monomeric ester chemistry, which really gives excellent moving viscosity reduction on your base polymer system. It'll really give excellent retention of elongation, hardness after air aging. So we're really looking for initial performance properties and performance after aging. In this case, ozone, oxidation, and outdoor weatherability. So this lowers the hardness. The Plastol P670 effectively lowers the hardness of the base compound. You'll have low volume change and weight change after fuel C immersion and lower elongation after immersion in the ASTM 902 oil. So after looking at those different polymer systems, a diagram that we really wanted to show was the internal combustion engine as it is today. We see that there's many different polymer systems that are going into it, many different parts of this internal combustion engine, and each of them needing different sort of requirements. Some might be directly exposed to oil, some might be exposed to more heat. Some might need low temperature flexibility because it's a moving part, while others may be more rigid. So in general, this is kind of how we see the breakdown of a lot of our different products. In AEM and HNBR, we might require a balance of that really high temperature requirements, while some might need more oil. We wanted to be able to contrast this with the transition to electric vehicles. All the parts that are circled in red here are parts that are at risk of being eliminated in an electric vehicle. Some of the parts, like a transmission seal and radiator hoses and transmission cooler hoses, will still be required to cool down a battery, but in general, it will not be a moving part. Really what we're doing here is we're going to be eliminating moving parts or things carrying fluids other than that transmission. So we want to be able to start discussions with companies like yourself to be able to understand better what the next generation of elastomers are in some of these internal combustion engines and what that transition looks like to EVs, and really want to be on the forefront of innovating in some of these new polymer systems, being able to look at the new extraction solvents that might be present when cooling electric batteries, and seeing what improvements can be made on that technology. So feel free to reach out to us, especially if you're developing on any sort of parts on EVs. We'd be happy to help and really try to jump into the next stage of innovation. So at this point, I'm gonna stop talking and transition over to Jim Kozlowski, who will introduce some of our magnesium oxide brand. Jim, take it away.
Thank you, Sean. Appreciate it. To conclude our product line today, I would like to speak to our Maglite brand of process aids. The Maglite brand has been an industry-leading name for decades. This high-quality magnesium oxide is produced through a precise seawater extraction process. The precipitate is calcined to the desired surface area, yielding various grades of magnesium oxide. This excellent quality and consistency are critical for elastomer applications. The high quality and batch-to-batch consistency are critical for optimal processing and cure rates in elastomers. Here's a graphic of Hallstar's line of Maglite products differentiated by activity levels. Depending on the elastomer and application, we can recommend a suitable product. For instance, a low activity Maglite Y is a great option for an elastomer system that requires a slow controlled cure rate. And a product such as the Maglite DRX would be more suitable for a faster cure profile. Here are typical properties of magnesium oxide. These characteristics and specifications can be found on a technical data sheet. The surface area is an approximate indication of overall activity. As the magnesium oxide is extracted from seawater, it is calcined to generate a particular surface area. The particle size is a measure of what percentage of material will filter through a 325 mesh. The bulk density is an indication of how the product packs together and flows. This may be a consideration when working with open or closed mixing systems. And since magnesium oxide is hygroscopic, the water content is very low. The surface morphology relates to how the magnesium oxide particles will act under the pressure of elastomer compounding. Some particles will break apart, creating more surface area and activity, and some will collapse, which reduces surface area and activity. Here is a graphic of Hallstar's surface area by product. At the top, Maglite DRX has the highest surface area with the highest activity. And Maglite LA has the lowest surface area and activity. As the magnesium oxide is being calcined, it reduces the surface area and activity. Once the magnesium oxide falls below 20, it is considered dead burned, which is not suitable for polymer grade. Here is a typical formulation using 3M's Dyneon FKM that RD Abbott supplies in Hallstar's Maglite and calcium hydroxide products. The Maglite would be added at 3 pHr and the calcium hydroxide would be added at 6 pHr. There is a wide variety of FKM grades, so please contact RD Abbott or Hallstar for a specific magnesia recommendation. For more information on Hallstar's plasticizers and Maglite products, please visit our website at hallstar.com or contact RD Abbott, myself, or Sean Neuenfeldt. We also have a LinkedIn page here and other social media. And if you have any questions about plasticizer, elastomer compatibility, feel free to reach out to us. I would like to thank you for attending And I'd like to hand the Q&A portion over to Tanya Mendoza.
Thank you, Sean and Jim. Those were excellent presentations. Thank you both. Great
Thank
job.
you.
Thank you.
Well, it looks like we have several questions already in the queue. So let's get started. Let's take a look. The first question is the PR 610 grade REACH registered?
For the 610 grade, I have to verify that, but many of Hallstar's plasticizers are going to be REACH registered. What we're going to want to do is make sure that we check the volume level that you need to be able to import that through, and make sure that everything lines up. Most of our polymers and our polymeric chemistries, we're going to have each of the monomers REACH registered or be able to import a certain amount. So usually we try to, when looking at REACH, we usually try to focus on polymeric chemistries and making sure that all those monomers are registered. So I'll have to do a review and make sure that the P610 is registered, or the chemistry that chemistry is registered at the volume you want. But yeah, most of our chemistries is going to be REACH registered or polymer exempt under REACH.
Excellent. Thank you, Sean. Let's see. The next question is, does Hallstar offer any recycled plasticizers, post-industrial or post-consumer? Great question.
Well, we don't have a lot of recycled plasticizers, so it's difficult to extract out a plasticizer after it's already been, I guess, made into or put into a polymer system. A lot of times ours are oils, but we do go and we'll take any sort of recovered. So if there's any unreacted monoesters or in our systems, or any unreacted glycols or carboxylic acids, we're going to recover those and we're going to be able to recycle those back through our system. Our Bedford Park facility that we're manufacturing the majority of our products at is going to be run all by renewable chemistries. We have a variety of completely bio-based plasticizers, so we do have a lot of sustainability initiatives, but it's a little bit difficult to recycle the plasticizer itself. But we have a lot of different ways that we try to really push sustainability.
That's actually a great segue to the next question. What sort of sustainability efforts is Hallstar focused on?
Yeah, a lot of the stuff we've been doing recently is focusing on bio-based development. So looking and seeing what plant-based raw materials we could do and try to mimic or improve the performance of a petro-based product. So not only are we trying to make plasticizers that are designed designed with plants, but we're also looking at different sort of bio-based systems that we could go and put ourselves into. So not only looking at how can we incorporate bio content into petro-derived elastomers, but how can we go and put these bio contents and really improve the performance of a bio-based base polymer, looking at PLA, PHA, some of these different new next generation bioplastics, really doing a lot of stuff on that, in addition to our green energy initiatives that we have going on at the plant.
That's fantastic. Thank you, Sean. The next question, we have a very specific one. What will be the best plasticizer for nitrile rubber where end application will be E30? For example, blend of fuel C and ethanol at ratio of 70-30. That's a little specific. But
I think it's a perfect example of a collaborative opportunity. I'm going to have to go in and see a lot more about the application to see if there's any low temperature recommendation or low temperature flexibility needs, or if it's just simply an oil extraction requirement, because we'd be able to very easily design or pull off a plasticizer off the shelf that has little to no extraction. But that's not the only requirement that would be necessary. So we would have to see, okay, what's a viscosity limitation? Do you have pumps to be able to incorporate a higher viscosity plasticizer? Are there any sort of chemical abrasion resistances? So it's a really good example of an opportunity to collaborate where we can go and spend half hour, and really drill down into what the best plasticizer is for this application. So what I would say to that is, I have my email. Let's set up a conference call on that.
Wonderful, great answer, which goes into the next question that came up. What kind of technical support can Hallstar offer for customer projects?
Yeah,
specifically to custom formulations.
Yeah, that's exactly what Hallstar really thrives on. So what we do here a lot of times is work with customers on a one-off basis to try to see if there's anything currently in our portfolio that meets your needs. And if not, we can go and develop a product with you for you. And so a lot of our products are one-offs. They're going to be a specific product made for a specific application for a specific customer. And so we go and we'll have sit-down technical talks with technical groups. We'll sign NDAs if needed, and being able to have that open source of communication to try to solve whatever technical issues you have. So if you have any sort of specific problem where you have a certain polymer or a certain ACN content, or have a certain issue that's really tricky, or a certain regulation you're trying to develop a product around, because there are so many niches to this field, we really encourage you to reach out to be able to have these one-on-one talks, really a technical based talk, to be able to find out which of these 100 plasticizers we have is best for you.
Thank you so much, Sean. And let's kind of switch gears here. Let's switch over to the Maglite product line. What makes the Maglite manufacturing process unique?
So for a magnesium oxide brand, something that's really unique about it is the processing that we do for the magnesium oxide. This is going to be manufactured globally. And so because of the seawater process, you get a very, very high purity magnesium oxide. This is going to be a very high purity of MgO. You're going to have a very low amount of any sort of inorganics in the system. You're going to be able to have a very consistent product because of the seawater process, and you're going to have something that's going to have a very controlled reaction rate. So depending on the grade chosen, you'll get a narrow distribution of particle sizes. You're going to get a uniform distribution of bulk density, and you're going to get a very predictable, consistent product every time. So using that seawater process, we're not going to expect really any changes in the seawater. And that process being consistent every time and globally sourced, you'll have a consistent, reliable, predictable magnesium oxide.
Fantastic. Thank you, Sean. I think we have time for one more question. And the last question is a list of FDA-approved plasticizers available?
We have a list of, it's a little bit dated, but I believe on our Hallstar website, we have a list of 21 CFRs that are some of our plasticizers currently meet. So when they have to be in direct contact with food, we would have to look at that on a product by product basis. There's a lot of 21 CFRs, depending on if it's a can coating or if it's going to be, depending on the packaging, depending on the polymer system, it's going to depend. But all of ours are going to be, they're all going to be TSCA listed, all of our chemistries, of course. But the specific FDA 21 CFR callouts are going to have to be done on a product by product basis. But when you traditionally go to these higher molecular weight polyesters, they're going to get more and more 21 CFRs to their name. It's going to be much better than a monomeric ester, which would be more prone to extraction.
Thank you so much, Sean. Great questions, everyone. We're nearing the end of our time today, but not the end of our conversation. There are a couple more questions still in the queue, so I'll coordinate with our technical team to ensure someone contacts you promptly. If you have any additional questions, please feel free to complete our online contact form at rdabbott.com/contact. That's rdabbott.com/contact. Now, if you're interested in attending more RD Abbott webinars this year, please visit our website at rdabbott.com/2022 webinars. Again, Sean, Jim, thank you so much for the excellent presentations. But most importantly, thank you, audience, for taking the time today to participate in our webinar. With that, we will close today's webinar, and we look forward to talking with you soon.
Thank you. Thanks everyone for your time.
Everyone.